All right, you guys, I wanted to go over the Unit 1, Chapter 2 notes with you. I hope you find them interesting, and let's get started. So, Chapter 2 talks about the history of astronomy. And in this drawing, you see Nicholas Copernicus that is observing a lunar eclipse in Rome about the year 1500. It looks like he's using a telescope. However, the telescope would not be invented for another century or so. So he actually is looking through a transit device that improved that naked eye vision of angular sizes of the moon and the sun. One thing that I hope that you remember about Copernicus is that he is the Polish astronomer that first introduced the idea of our solar system not being geocentric, but rather heliocentric, meaning that the sun was in the center, as opposed to the Earth being in the center as previously believed. So in chapter 2, we are going to go through basic information about ancient astronomy and then through the two different types of models of the universe, first being the geocentric, the second being the heliocentric, which is currently accepted as the true model of the solar system. And then, of course, we are going to wrap it up with some basic information about modern astronomy, follow up by a little bit of physics, very basic information on the review of the laws of planetary motion, and then Newton's laws past that. So in terms of ancient astronomy, we are familiar with the fact that people have been checking out the night sky as long as there have been people. They were trying to come up with ideas and models that would explain the movement of stars and what they believed were brighter stars that moved faster across the night sky than the background stars. Well, now we know that those fast moving stars are not really stars, they were planets that they were observing. But needless to say, people were very excited and interested in the night sky. So in this slide here, we have a couple of pictures of the Stonehenge, and you watched a quick video on Stonehenge and how people used it in terms of aligning it with the summer solstice. And that's what we're seeing here in this smaller image on the slide itself. This is one of the example of observatories in the Americas. And the image here illustrates the Bighorn Medicine Wheel in Wyoming that was built by Indians and has the features that roughly aligned with rising and settings of the sun and other stars. Looking at some more examples of ancient astronomy, here we have the Caracol Temple in Mexico, which has a lot of its features aligned with astronomical events. In addition, a lot of the structures built by the Mayans were actually affiliated with the stellar phenomena. They were really fascinated with astronomy. In particular, they had this fixation on Venus. They were really good about collecting data on our sister planet Venus. So we know that ancient astronomers observed the sun, the moon, and the different phases of the moon and how they changed over time, the stars, and then the planets that are visible with the naked eye. So we have Mercury, Venus, Mars, Jupiter, and Saturn. this is pretty much an image showing you how during those dark ages science was being done and information was preserved and the new discoveries being made by early astronomers. So obviously, originally people thought that our solar system was based on the geocentric universe, meaning that the Earth was right in the center of the universe. Very often, that idea was driven by religious beliefs. Oftentimes, it was limited, scientific discoveries were limited by the Catholic Church because science had to follow what was written in the Bible. And in the Bible, it stated that the Earth is the center of the universe. So people in those times, those early astronomers, were trying to build and come up with those models that would fulfill the idea of Earth being in the center of the entire universe. One of the issues that they ran into was the retrograde motion of planets, and this is what we are seeing here in the image. The top image is a long exposure image showing you the movement of planets, and the bottom image gives you the background of night sky with Cancer and Leo constellations being present, and then we see the movement of Mars as it moves. It looks like between January to perhaps November through June. And you notice that if we track that along, there is a kind of this curvature going on that begins around January 1st, and then it appears that Mars is moving backwards as we go from January 1st to February 1st, and then through March 1st, and then April 1st comes around, and the planet actually appears that it's going to move again towards that preferred direction. So that was very puzzling for scientists because they couldn't explain why would a planet go through this retrograde motion. And they went into some big trouble to try to explain why that was happening, why were those observations made, and they had a hard time coming up with the scientific explanation, the mathematical explanation why that would happen with Earth being in the center of our solar system. So we know that in here we have the distinguished the difference between inferior and superior planets. And the idea was that the inferior planets were Mercury and Venus, and then superior planets, Mars, Jupiter, and Saturn. Those were the 5 planets that were visible with the naked eye. Okay, an inferior orbit will lie between Earth's orbit and the Sun, where a superior orbit, such as the orbit of Mars, Jupiter, or Saturn, lies outside of that Earth. The points noted on the orbits will indicate when the planet appears to come close to the Sun during conjunction, or is opposite of the Sun in the celestial sphere, or it's in opposition. And that's what those the bigger image here shows you. So some of the early observations that were made during the formation of the geocentric universe was that the inferior planets never were too far from the Sun. Venus is oftentimes referred to as the morning star or the evening star because it's easily visible during sunrise and sunset, where the Sun does not overpower the planet's reflection of the sunlight, and we'll get to that in just a minute. They decided that the superior planets were not tied to the Sun, and those are the ones that gave them trouble because those were the ones that would exhibit the retrograde motion over a period of time. They decided or observed that the superior planets were brightest at opposition, and the inferior planets were brightest near inferior conjunction, meaning that they were close to the planet. So, like I said, they had to be creative. Here in this image, we have the Earth being in the very center of the solar system. And this is Ptolemy geocentric model of the inner solar system, where this model was pretty popular across, most of Europe prior to the Renaissance. So, like I said, there was only 5 planets that were visible to the naked eye, and they had to be creative to explain those motions and that retrograde motion of planets. So the closest neighbor in space was considered Moon, followed by Mercury, and then we had Venus go beyond that. And if you notice with Venus, Venus did not only go around the Earth in its orbit, but also had this weird loop-de-loop that it would do at one point in its orbit. Beyond Venus, we have obviously the Sun. And then beyond the Sun, we have Mars, that again, not only did it go in a large orbit around Earth, but it also was going in smaller circles that's drawn here on this image. Jupiter, again, very similar pattern, was going through this loop-de-loop pattern as it orbited the Earth, and so did Saturn. So, like I said, they had to go through a lot of trouble to try to explain those different motions in the night sky. The Copernican model of the solar system explained both the issues that were, hard to explain in the geocentric model, meaning that the brightness of the planets as they moved in their orbit, as well as the phenomenon of the retrograde motion. Here in this image, we have the Earth and Mars shown in their orbits around the Sun. And when Earth and Mars are relatively close to one another in their respective orbits, so if you start with position 6 in this image, Mars seems very bright because we are fairly close to it. When they are when they're farther apart, for example, when we're looking at position 1, Mars seems dimmer, again, because it's farther away from us on Earth as the viewer of the planet. Also, because the line of sight, so if you follow the light blue lines on this image from Earth to Mars, as we move through the entire orbit, so throughout the entire Earth's year, we start in number 1, so let's say in January. If you follow the lines from position 1 for Earth and position 1 for Mars, you will see the third line, which is the furthest up away from the Sun that's indicated on this image. And I don't know if you can see my mouse in here. So this would be the line, the position 1 right here. As we move from the position 1, so January for Earth, and position 1 in Mars's position, this is where Mars would appear for the observer in the night sky. As the time passes by, remember Earth moves, and now we are going to look at February 1st, for example. Mars has moved a little bit in its orbit, so it's right here. This is where Mars would appear to the viewer on Earth. March 1st, we have Earth in this location here in its orbit. Mars is over here, and then we are going to view Mars in the position in the night sky as viewable from Earth. Now, if you notice in position 4, we are catching up to Mars in its orbit, right? So Mars is here. We're going to view Mars in the night sky in this location. Now in position 5 through 7, now Mars is going to appear to move backwards, right? Because in May 1st, we are slowly catching up with Mars. It is going to appear in the night sky here. Position 6, we are perfectly aligned. And now if you notice, between position 5 and 6 on the apparent motion of Mars line, now it appears that Mars have began to move backwards. Again, from our perspective, seeing it from Earth. Position 7, Mars continues to move backwards in its orbit as it's seen from the observer's perspective on Earth. Now, in position 8, we have moved past Mars in its orbit, so now Mars appears to move back in the preferred direction, and that continues in September, right, in month 9, in October, November, and December, and so forth. So I hope that makes sense, showing you kind of where this idea of retrograde motion comes from. So kind of the discovery that took place with placing Earth in or outside of the center of the universe explained a lot of those things. So we know that Earth is no longer the center of everything, right? The center of the Earth is the center of Moon's orbit. So the Moon is going to orbit in a perfect circle around the Earth. Copernican model also said that all planets revolve around the sun, and they revolve in a perfect circle, right, around our star. He decided to be open about the fact that the stars are very, very far away from the Earth than the sun is. The apparent movement of the stars, so what you would see on your star chart, is due to the fact that the Earth is traveling in its orbit around the sun throughout the 12 months of the year. The apparent movement of the sun is because of Earth's rotation. It's not because we are placed in one location in the solar system and the sun is rising in the east, setting in the sun as it goes around the planet. It's actually the other way around. And then, of course, the retrograde motion was explained already, and it is because of the motion of planets around the sun. Moving on to the introduction of modern astronomy, and that began with the invention of a telescope. So Galileo built his own, and he made a few observations that were essential to the study of astronomy. He discovered that the moon had mountains and valleys, that the dark parts of the moon were not filled with water. They were actually valleys that were shadowed as the different angle of the sunlight was hitting the surface. He discovered that the sun had sunspots, and because of the data collected on sunspots, Galileo was actually able to figure out that the sun was rotating, that it wasn't just stationary in one spot. And hopefully this semester at some point we can get out and actually observe sunspots outside. Hopefully we'll get some nice bright sunny days once it's nice and warm outside. He also discovered that Jupiter has moons, and he was able to draw images of the different locations of the moons as it's shown here on the slide. And he also discovered that Venus goes through phases, and it is due to the fact that it is revolving around the sun. He also was known for making remarkable sketches of Saturn, as well as the Orion constellation as that was, that's what he did. So in this image here, we have the different phases of Venus that could not have been explained if Earth was in the very center of the universe. So that's what the bottom picture is showing you, is the image of Venus as it goes through its phases, with Earth being in the center of the universe. The Venus's orbit is indicated on this image here, and the Sun's orbit is indicated beyond the orbit of Venus. And if you notice, if we have Venus that's between the Earth's observer and the Sun, half of the planet that was illuminated would always be facing away from us. So we could only see either very teeny tiny sliver of Venus as it reflects the sunlight, or we may not see it at all. That could not have been explained by this geocentric model, knowing that this is not what we're seeing, because we're actually seeing the entire system of Venus's phases, and that's what the top image is indicating, with the Sun in the center and the Venus orbiting between the Earth and the Sun itself. We can see, as it's indicated here in all these images of Venus's locations as it goes around the Sun, is that the part that's illuminated is going to vary over time. And there are times where we should see Venus pretty much in a full Venus phase, right? If you think about a full moon phase, full Venus phase would be one that we would be able to see almost the entire circle, the entire half that's illuminating facing us. That could have never happened with the Sun having been beyond the orbit of Venus. And then, of course, we get into the laws of planetary motions, and Kepler's laws were essential to the study of astronomy. Kepler actually took data that Tycho Brahe was able to collect, and Kepler utilized that data to come up with his laws of planetary motion. With the first law stating that planetary orbits are ellipses. They are not perfect circles. Planets do not travel around the Sun in perfect circles, and as it was initially thought was the case. The Sun is one of the focus points within the orbit. I'm sorry, not within the orbit, within the ellipse. The second law indicated that there is these imaginary lines that could connect the Sun and the planet's location as it goes in its orbit. So, for example, if we were to measure the area of a triangle indicated in this picture as triangle A, it is going to be the same area as the planet that sweeps the area C. Now, the very interesting part is that the time it takes for the planet to sweep the area A is exactly the same as the time it takes for a planet to sweep the area B and C. So if you think about it, in area A, the orbital path that the planet needs to travel is much, much shorter than the orbital path that the planet takes in location C. And they take the same exact amount of time. So what does that mean? That means that the planet must move much slower in location A than it does in location C. In location C, the planet needs to move much faster to travel that longer distance within its orbital path within the same amount of time. The third law indicated that there is a relationship between the planet's period of orbital motion there's relationship between that and the cube of semi-major axis. And this will make more sense once we get into a Mercury study that will really outline those three laws of planetary motion for you. So here is just like a bonus slide for you. However, it has two very important terms on it that you will need to be familiar with. Perihelion is going to be a location of a planet when it is the closest to the sun. Aphelion is going to be one when the planet is the farthest away from the sun. Because again, the orbits are not perfect circles, so at some point the planet is going to be closer to the sun than others. Now, oftentimes people will get confused and they think that seasons are actually affiliated with how close or how far away we are from the sun. And this is as far from the truth as one can get. We are actually the closest to the sun in our orbit in January. So it is definitely not warm in January. We are the farthest away from the sun in July, where you would think, well, if we're really far away, then it should be much colder. That has nothing to do with the distance to the sun itself. Another term that you need to be familiar with is the astronomical unit. And the astronomical unit has been derived based on the distance that there is between the average Earth's distance from the Earth to the sun. I say average because, again, it will vary based on where the Earth is in its rotation or in its orbit. Oftentimes, we only use astronomical units within our solar system because the unit is not big enough when we talk about distances between galaxies or between stars. At that point, we would use light years. Okay. Now we have obviously more precise instrument that we can measure distances between different objects within our solar system. Radar is one of them, where we can have an emitted radio wave and then time it how long it would take for the reflected radio wave to get back to us. Knowing the speed of light, and we know that radio emissions are traveling at the same speed, we can figure out the distance, knowing the time and the speed of that wavelength. Finally, we can look at some Newtonian physics, and we are not going to get too much into that, but more of a review of the three Newton's laws. And one thing that you need to understand is that laws of physics apply just as much within our solar system as anywhere else. So the laws of the Newton's laws, especially if we think about gravitational pull, that is true and that can be applied anywhere in the universe. It's not only to be used within our solar system. So Newton's first law, and I hope this is a quick review for you, states that an object will will remain at rest, and an object that is in motion will remain in motion unless there is another force acting upon it. Newton's second law indicates that there is a relationship between the acceleration and the force and the mass of an object. For example, if you think about going shopping and you have a cart that's empty, you will not need to apply a lot of force to accelerate that empty cart. Now, if you fill that cart with water, for example, with bottled water, you will need to apply a lot more force to that mass to accelerate it to the same rate, because now we have much larger mass. Newton's third law is the action-reaction law, which states that when an object exerts force on another object, that second object is going to exert an equal and opposite force. On the Earth's surface, acceleration of gravity is approximately constant. It will vary from place to place. Let's say if you're on top of Mount Everest, you might expect a little lower gravitational pull than you were in the deepest mine, right? So a ball thrown up from the surface of a massive object, such as our planet, excuse me, it will be pulled continuously downwards by the gravity of that planet. In addition, that ball is actually pulling on the planet. Now, obviously the planet is not accelerating towards the ball is accelerating towards the planet because of the difference in mass. And this is where the two masses will play a role, right? We have the gravitational pull, the gravitational force between two bodies, and there is a mathematical representation where we can calculate the force of gravity between two objects. And there is a relationship which is inversely proportional to the square of the distance between those two masses. Obviously, you will not need to memorize the value of G if we ever need to use it, and you will need to calculate the force of gravity on your upcoming exam. I will give you the constant for gravitational pull, the gravitational constant G that is indicated in this formula. So M1 and M2 represented two different masses of the two objects that we're calculating the gravitational pull between. R squared, sometimes it's also written as D squared. It's the distance between the centers of those two masses. So for example, if you are measuring the mass or the gravitational pull between the Earth and the Moon, you will need to measure from the center of the Earth to the center of the Moon, not from the surface of the Earth to the surface of the Moon. So just keep that in mind. Kepler's laws are the consequence of Newton's laws, because now they had that mathematical background to be able to explain those motions within the solar system. And we know that now the sun is in one of the focus points within the planet's orbit. Okay, I'm going to come back to that when we are actually talking about the relationship between the sun, the Earth, and the Moon. So we are not going to worry about this slide here. There's three different speeds that we can look at depending on how fast you launch an object into the atmosphere. It can have a couple of different paths, right? It can be returned to the Earth, right? If you throw a ball up in the air, chances are it will come back down because you have not thrown it fast enough. Now, sometimes if you throw it fast enough, it may get into the orbit, right? And if you throw it even faster, it will actually have enough speed, enough velocity to go into launch into space. Okay, I am going to not talk about the summary of chapters. You can pause this video and copy the information down if you're copying those down. If not, I will scroll down to the last slide, and that will conclude our lecture. And I am looking forward to seeing you in class.